Okay, so I am looking at page number 69. Remember that exponential growth or decay happens depending on the value of b in the setup formula, a times b raised to the power of x. So b is a multiplier, and b tells you everything that you need to know about whether or not something is growing or decaying. If b is bigger than 1, then it's growth, and it looks like this. And if b is between 0 and 1, then it is decay. You can't spell decay apparently. And it goes like this if you're looking from left to right. You should be able to just identify whether or not an exponential equation is growing or decaying just by looking at what's in the spot that is b and seeing if that number is greater than 1 or between 0 and 1. For instance, 2 is greater than 1, so this is growth. 5 is greater than 1, so this is growth. 1/3 is between 0 and 1, so this is decay. Oh my god, I don't know why I can't keep remembering to put the C in there. 1.3, greater than 1, this is growth. 0.6, this is decay. There you go. I didn't forget the C that time. Original amount of carbon-14 was 300 atoms, and the half-life is 570 years. Write the equation to represent the amount of carbon-14 left after X years. So you're going to go ahead and do that. And then find out how much is left after 2,500 years and after 10,000 years. So this is a time where you should put it on pause and do this example. It's just like the ones from the page before at the end of the last video. And then come back and compare your answers to mine. So write the equation to represent the amount of carbon-14 left after X years. So our beginning population is 300. Our multiplier is half, the half-life. And our exponent is how many years out of 570? I think that is 570. Oh, nope, it's 5700. There's a 0 that's hidden there for me. Okay, so that's my equation. If I were to go ahead and put this in Desmos, I will first plug in 2,500 years for x, and then I'll plug in 10,000 years for x and see what I get. So let's put this in Desmos. Okay, so here is the answer to my first question. How much is left over 2,500 years? I plugged in 2,500 for x. It would be 221 point lots of things. And then after 10,000 years, we've had more than one half-life. So I have 88.9 blah, 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 that much left for carbon-14 atoms. Let's look at the next page. If a starting population is 12,500 and it doubles every 20 minutes, write an equation using X hours. Notice that we have two different means for measuring time. They want us to write an equation that talks about hours, but they're telling us that something happens every 20 minutes. You have to ask yourself, how many 20 minutes happen in an hour? 20, 40, 60. So this is doubling 3 times every hour, right? How are we going to write that up? Let's put our f of x equal to the starting population times the multiplier raised to the power of 3 times every hour. You always have to figure out how this would relate to how many hours. Okay, so that's not too bad, and that's something that can happen. Finding a model. Okay, so what happens if you end up being given information in a table and you're asked to find an equation, an exponential equation that matches it? Remember that you have to just find two numbers, the starting population and the multiplier. The starting population is usually pretty easy to identify because it starts at 0 hours or 0 days or whatever this represents. So for this, I can plug in 15 for A. I have to figure out the multiplier. In this case, I can see if I multiply 15 by 4, that will give me 60. And 60 times 4 gives me 240. And 240 times 4 gives me 960. So it must be 4. But what if we don't know if it was 4? What you can do is you can actually, as long as they are two pieces of data that are separated by 1 unit, you can take the second and divide it by the one that's before it, and that will tell you what the multiplier is. So that's another way to figure it out. Just kind of cool. Okay, so let's look at the next page. You're asked to find the models for the following tables. Remember, both times you're going to use the setup for starting population and multiplier. So I always write this out first. Starting population for A is easy to identify. 0 hours or days or minutes. The population is 16, so A must be 16. I have to find B. It's not as pretty as the last one, but I did tell you that if your data is 1 unit apart, so between 0 and 1, that's 1 unit, you can take the second piece of data and divide it by the first. This is going to give me some kind of decimal. Let me just check this real quick. 36 divided by 16. That's 2.25. So my multiplier is 2.25. Let's look at B. One thing I'm noticing about B, it's a little bit different from the last ones because I can see that this is decreasing. So that's kind of interesting. It looks like it's decreasing every 4 years. So what I'm going to do is I'm going to come up with a starting population. That is going to be 1,500. I'm going to find my multiplier. So I can see that this happens every 4 years. So I'm going to do this x over 4. And I'm going to take the second piece of data, divide it by the first. 300 divided by 1,500 is going to be 0.2. Okay, so looks like every 4 years my population reduces by 80%, or you could also describe that as 0.2, 80% decrease. Notice again though that like I did divide by this one jump. In this case, it's not as much like A, because A, we were looking for pieces of data that are 1 unit away from each other. In this case, it happens every 4 units. So that's why what's the word I'm trying to use? I address that by putting x over 4. So every 4 years is kind of like the same jump as 1 unit would be in A. Okay, let's look at the next page. Okay, a few different types of questions that you could be asked when it comes to looking at exponential models. Here's a graph that's showing an exponential model. It's asking if it's increasing or decreasing. You always will know if you read it from left to right. This is going downhill, so we're going to say decreasing. Example of exponential growth or decay. It must be decay because it's decreasing. The f of 2 is asking us to find 2 on the x-axis and follow it up and over to figure out what the y value would be. In this case, it looks like it's like 15. What x value will make a f of x value be 10? So I had to start at 10, follow that over and down. I'm going to estimate that an x value of, say, 2.6 will give me an output of 10. The last question is asking you to estimate the y-intercept. This looks like it happens at 0, 50, right between 40 and 60. Take a moment and do the next example. I want you to pause. Come back after you've done this to check your answers with mine. Okay, is the graph increasing or decreasing? Go to left or right. It is increasing. And if it is increasing, then that means growth. H of 5 gives me 20. Well, x value gives an output of 100. Looks like 15. When x is 15, h of x is 100. Estimate the y-intercept. That happens right here between 0 and 20, so it must be 0, 10. If you're estimating, your numbers might be a little bit off from mine, and that's okay if that happens. It's mostly an opinion anyway. These aren't very, very, very gridded and detailed for us to get very specific answers, but if you approximated close, then you are good. So this is the end of this video.